Hello, everybody. This is the time of our Prague seminar for mathematical physics. I'm very glad I can announce this talk and our speaker who is gonna to deliver it. It is Richard Szabo, who came to us from the far countries outside the European Union. And yeah, we are pretty happy he accepted our invitation and is apparently prepared for us very interesting topic. At least I guess so because of the interesting title. So the title is BV quantization of noncommutative field theories. Richard is a professor and a researcher from Heriot-Watt University in Edinburgh, and I hope this is all I need to say. And now I the floor for him to talk something interesting.
Thank you. Thank you for the nice introduction. The slide's going to come up. Right. Okay. So yeah. Thanks for the introduction. It's a pleasure to be here. I'd like to especially thank Brazil for inviting me here. And I've been here for a month. I leave tomorrow, but it's been fantastic talking with people, and it's a great atmosphere here to work. So a very enjoyable and productive month. I'm gonna talk about something which I hope is reaches out to the different tastes and specialisms of the group here. It has to do with something I've been working on for the past 4 or 5 years now. Something actually that I'm very excited about. And it has to the quantization of non-commutative field. So I'm going to start off with some physics motivation to what I'm doing. So I'm a physicist. I come at this from a physics angle. If you don't understand anything in my introduction, don't worry, because the rest of the talk is all mathematics. Okay. So, but I do want to give some kind of a context, and for me, I think the physics context is really the driving force behind this this project. Okay, so the motivation behind this comes from some excitement in physics that was sparked from string theory well over 20 years ago now. This is the topic of non-commutative field theories. And so I come at this from a string theory background, but I should mention that the notion or the topic of non-commutative field theories is quite broad. They appear as effective field theories in many systems, ranging from high energy physics to condensed matter physics, and they're often motivated as being some kind of toy models, toy scenarios for what we might think of as physics at the Planck scale. So something that might be a toy model for quantum gravity. That's where we think that space-time might become non-commutative at short distance for us. For whatever reason you want to study them, let's move on. So the standard example that comes from string theory is if you look at just a flat space, you look at open string quantization in this flat space, and we got a background B field. So this is a two-form field. It's a constant two-form field. We assume it's non-degenerate, so inverse gives us a bivector, a constant bivector. And then so you have a bivector, it's a Poisson structure, you can quantize it and you get the famous Moyal-Weil star product. Okay, so you can do that mathematically, but from a physics perspective, this is really a calculation you see when you calculate correlation functions of open strings in a two-dimensional quantum field theory. You find that the interactions between the vertex operators are governed by just replacing products of your fields everywhere with this star product. Okay, so mathematically, it's clear what it is, but the excitement was that this really comes out from a physics calculation, an honest, precise physics calculation. Okay, so now open strings end on D branes. We know that in the standard case, the low energy dynamics on the D brane is governed by a gauge theory. So now this gauge theory gets deformed to something called a non-commutative gauge theory. See, the story goes back to well over 15 years ago, and it's really what sparked a lot of excitement in the topic. So that's for a constant B field background, or if you wish for a constant Poisson bivector, you can extend this to curved scenarios where your D branes are curved, still living in flat space, but now they have a non-constant B field, so they'll have a non-constant Poisson structure, and this B field might not even be a closed two form. You can even allow for that. This gives us a three form that we call H flux. And so again, in the language of Poisson structures, this would not be a Poisson structure, but it would be a twisted Poisson structure. So it leads to some source of non-associativity. And some well-known curved examples are well, D branes whose target spaces are group manifolds. So these are Western-Witten models. And more recently, these theories with the non-constant B field have appeared in sort of deformations of the ADS-CFT course, if you know what that is. So if you take the standard string ADS5 cross S5 sigma model and you deform the target space in a special way, you still get an integrable two-dimensional sigma model. And then you ask, what is the holographic dual to that gravitational theory in the sense of ADS-CFT, and that turns out to be a non-commutative gauge theory. Okay, so that's where these crop up. So what is the sort of issues here? Well, the case with the constant B field is by now well understood. It's a very standard example, and it's straightforward to deal with. But we still don't have a good grip on how to work with non-constant Poisson structures. So these cases I mentioned about curved D branes, or even worse, we don't know how to deal with twisted Poisson structures. We know some things, but we don't have a fully fledged way to describe non-commutative gauge theories in that case. So what are some of the problems that come up? Well, in the case of Poisson structures, I mean, you can always quantize any Poisson structure using the quantization formulas. So there's always a star product available. But of course, now if the bivector is not constant, you lose things like the Leibniz rule for the multiplication, for instance, because now the star product actually is position dependent, so you can't just pull the exterior derivative through it. So it's quite trivial, but that's one of the issues. The exterior derivative is no longer a derivation of the algebra of functions. So this really obstructs the naive exterior derivative from defining a good non-commutative differential calculus. Or in other words, what is a notion of a differential graded algebra? This is the non-trivial thing to do. And one of the consequences from a physical standpoint, we can, in non-commutative gauge theory, you can define infinitesimal gauge transformations. And then the naive closure rule for the gauge transformations don't hold. So they naively will not close on the algebra. So there's been some attempts over the years, but in dealing with this. And more recently, the formulas of homotopy algebras has been suggested as a way to go around this, because homotopy algebras give us a systematic means of constructing field theories in general. Okay, so it's been suggested that these do offer a nice arena for constructing non-commutative gauge theories. They'll deal with these issues of trying to build up some notion of a differential graded algebra and some kind of closure of gauge transformations. But this approach also meets with several problems. So it's only really understood how to do this very generally at what I call the semi-classical level. And what I mean by semi-classical is that the star product and these kind of star commutators that appear there are quantizations of Poisson brackets. Okay, so if you look at the lowest order limit of these star commutators, they're Poisson brackets. And actually, if you restrict just to the level of Poisson brackets, you get a theory which makes sense in the sense that everything closes within the semi-classical approximation. And you can go and do this construction. So at this semi-classical level, you can do everything. But the question of really doing things at the full level of a non-commutative gauge theory is not understood. And that's just as an aside, at this level of this semi-classical level, what you're looking at is a problem of constructing a differential graded Poisson algebra. And that's a nice sounding word, but it's actually a non-trivial thing to construct, starting from a general Poisson. And that was something that was looked at for many years during the 2000s. But that's the problem essentially one tries to address. And the issue with this approach here is that for a general Poisson structure, you need infinitely many L-infinity brackets. And that's okay, because this is what L-infinity algebras do. They give you infinitely many products, but it's somehow an unsatisfying answer from the physics perspective. And it suggests that we're trying to kind of cram a theory into the L-infinity algebra formalism, and it maybe doesn't want to be put into that formalism. At least that was the philosophy that we used. So we had that in mind. We didn't like the infinitely many brackets. We especially didn't like the semi-classical limit. And so the idea was to go and look at theories where instead of just using a standard homotopy algebra that controls the field theory, you deform the homotopy algebra. So we introduced this notion of what's called a braided L-infinity algebra. And I'm going to explain what that is. And what these do is they construct what I'm going to call braided field theories. These are theories that are going to be equivariant under the action of some given triangular Hopf algebra. And the fields in this theory are non-commutative, but the non-commutativity is controlled by a braid. Okay, so I wrote braided non-commutative. I guess the better word is braided commutative. But a commutative up to some braid. Now, this idea of braided field theory in itself is not new. The kinematical aspects of what you could think of as braided gauge symmetry, braided gauge transformations, go back to over 30 years ago. And the techniques that are used in the construction of these theories are borrowed from approaches to understanding how to define non-commutative deformations of general relativity. So you can try to get some notion of what a non-commutative diffeomorphism symmetry is, and ultimately a theory of non-commutative gravity. And so the actual the origins of the ideas there are not new, but putting them together under this umbrella of thinking of field theories in the language of L-infinity algebras is new as far as I am aware. So that's technically what we do. So what does physics tell us? How does this jive with what we would expect from physics? Well, I don't know. I don't know yet. There are hints in the literature which looked at how to think of the symmetries of closed string amplitudes using Hopf algebraic techniques. So that might be one place to look for these types of braided deformations. And also braided deformations seem to underlie these ADS-CFT dual gauge theories that I mentioned before that come from integral deformations of ADS5 cross S5 sigma models. Okay. So the physics, there are hints that these may have a realization physically, but this is something we don't quite understand right now. Okay, so far that's all classical stuff. Now, what about the quantum theory? How do we quantize this theory? So the problem is we have these fields now, and they're braided commutative. So somehow we've got a braided space field, whatever that is, right? What does it mean that you've got a braided space? And it's not clear how to define a path into this space, because it's not clear what the if you're a physicist, you would try to quantize by writing down a path integral. But now I don't really know what the configuration space is of my path integral, because I don't really know how to make sense of a braided space of fields. I don't know what the path integral measure is. So it's not clear how to quantize the theory. In 1999, Robert Oakland wrote a very interesting paper, which he looked at a very algebraic way to think of quantum field theory. And he also called it braided quantum field theory. And his approach was based on giving an algebraic description of a version of braided Gaussian integration, and then ultimately the braided Wick's theorem. Okay, so Wick's theorem in quantum field theory is Gaussian integration, right? Okay, so he gave a very algebraic way. This is a way to describe perturbative correlation functions in braided quantum field theory. But he only dealt with scalar. So his approach could not deal with theories that have gauge symmetries. Whereas our approach, based on L-infinity algebras by construction are sort of there to take care of gauge symmetries. So that brings me to the goal of this talk. I want to apply some kind of a modern, first of all, describe an algebraic approach to quantization that does not rely on the notion of a functional integral. And it's not because the notion of functional integral just isn't mathematically defined at present as it is, but it's just because I don't know how to generalize that way of quantizing. So I got to show an algebraic way to quantize ordinary theories, and that will generalize to this braided setting. So I'm going to look at the Batalin-Velikovsky formalism, which has been around since the early 1980s. But I'm going to look at it in its modern incarnation. That's due to the work by Costello and Will. I've had people come down on me when I say this is the modern incarnation, because I start going through it and they say, well, that's just BV. And it is just BV, but it's formulated in a slightly different language that perhaps emphasizes the algebraic aspects of the feature more than the analytic problems. So first, I'm going to do that for the conventional non-commutative field theory, show you how it works there, because that's just the standard BV formalism. And then I'm going to show you that there's a braided version of this theory, which is actually very, very straightforward to write down. And that's the theory which is going to capture the perturbative quantization of braided field theory, and it gives explicit calculations of correlation functions without ever having to think about what is the path into. So that's the goal. That's what I'm going to do. That's the two parts of my talk. I'll start by telling you about this BV formalism. I'm going to do an example, an explicit example, and then I'll do the same for the braided version. Now, in this talk, I want to do everything as precisely as possible. So I want to avoid the analytic complications that come in with continuum field theories. I don't want to have to deal with analysis. So I'm going to work with these things called fuzzy field theories. These are theories with finitely many degrees of freedom. Everything is inherently finite dimensional, and I don't have to worry about any analysis issues. It's purely algebraic treatment. So this will amount to looking at a finite dimensional and purely algebraic BV formulas. An extension to continuum models are possible, and we've been working on that. There's a series of papers starting from 2 years ago and one just 6 months ago or so. But this is at the level of the physics level of rigor, and if you want to do it properly, of course, there's a lot more work to be done. So that's an outline of what I'm going to talk about. Okay. So that's all the physics you need to know. Now we're just going to do math. Okay. We're going to build up quantum field theory in the BV form. So we start with the field. With quantum field theory, you start with free fields. So we start with what we mean by a free BV field theory. Okay. So a free BV field theory is a triple, E, Q naught, and then some brackets. What is E? Well, E is a graded vector space, a Z-graded vector space. Of course, I'm going to usually demand that it's bounded so that it's finite dimensional, but it's a Z-graded vector space. Now, if you look at the component and degrees -1, 0, and 1, then in the, thinking ahead to the BV language, these would encode the ghosts, the fields, and the antifields of your theory, respectively. And then higher degrees will, include sort of higher symmetries, ghosts for ghosts and things like that. So that's what E is. It's a graded vector space, and then Q naught is an operator on E, which is a differential. It squares to 0, and it's of degree 1. So I'm using cohomological conventions for the differential here. So that means the pair E and Q naught form a cochain complex. And just as an aside for the mathematically rigorous, the cochain complexes form a symmetric monoidal category. Okay, so you can take tensor products of cochain complexes. So it makes sense to talk about tensor products in this theory. Okay, and then finally the bracket there. So this is you think this is an inner product. Okay, so it takes a tensor product of the cochain complex with itself, gives you back a complex number. It's non-degenerate, it's graded antisymmetric, so everything here is understood in a graded sense. It has degree -1 and it's invariant under Q0. So it's like an invariant inner product.
The vector space that you start is over C.
I'm sorry?
The vector space that you consider is over C.
I'm working over C. Yeah, you can work over any field of characteristic 0, but I'm for physics applications, I look at the field of complex numbers. Okay, so again, in thinking about, if you know the classical BV formalism, this would be a symplectic structure on your theory, which is what the BV formalism gives you, and it's -1 shifted. So there's this kind of weird shift of degrees. So we're going to come to that in a moment. So what this object does mathematically is, what you have is a field theory, and you want to think about the space of fields, but that space of fields might have symmetries, right? Might have gauge symmetries, and you want to define some way to quotient out these symmetries. You also want to, in the classical theory, even you want to quotient out by like the equations of motion. So you want to make sense of how to do these quotients, because quotients are ill-behaved. And this gives you a formalism for doing that. It doesn't just describe the space of fields, it describes the space of fields with symmetries and certain types of resolutions of what would otherwise be singular quotients. So it's called a derived space of fields, in this case of true fields. Okay, now in the BV formalism, we don't work with the fields themselves, but we look at functions of fields. And I'm always going to think in terms of polynomial observables, so polynomials in my field. So the type of observables of the theory are going to be things that live in the symmetric algebra of the vector space dual of this underlying vector space. So just take the tensor algebra and quotient out by the graded symmetry requirements. Okay, and under this pairing, which I said has degree -1, you can replace the E star by E shifted in degree by 1. So it just means that when you look at the components of E square 1, you have to shift degrees down. So don't worry too much about that. But there is this shifting of degrees that happens here. So the observables form a triple now, this symmetric algebra. Q0 you can extend to sim. Okay, because as I said, you can take tensor products of cochain complexes. So the extension of Q0 to sim, I just use the same symbol. And now there's a bracket here. Okay, so this bracket there is something called the shifted Poisson bracket, because the degrees are shifted. And on primitive elements in E of 1, it's just defined by taking the cyclic, this pairing of the two elements, and then multiplied by the units of the symmetric algebra. And then extending that to arbitrary symmetric products using a Leibniz rule, which I'm going to come to in a moment. And this defines something called the P0 algebra. Okay, so what are the axioms of P0 algebra? Well, so this is something like a differential graded Poisson algebra. Except it's shifted. It's -1 shifted. That's why it's called the P0 algebra. Okay, so there's a compatibility condition with the differential. okay, which looks like the Leibniz rule you would write down. There's a graded symmetry condition, and that's what looks kind of weird, right? Because you would expect to see graded anti-symmetry for a Poisson bracket, but it's -1 shifted, so you actually see a symmetric bracket. Then there's a version of the graded Jacobi identity for this bracket. And here, when I write plus or minus, I mean there's some sign factor that depends on the grading of your elements. I'm just not going to write the formulas on this explicitly. And then finally, there's a Leibniz rule or derivation property for this bracket. Okay, so that's a P0, or something like a differential graded Poisson. Okay, that's the free theory. Now we want to work towards putting in interactions. We want interacting theories. And this is where the L-infinity algebra is now coming. Okay, so what's an L-infinity algebra? So we take this cochain complex that we have, and now I shift the degrees again. So there's this kind of weird shifting the degree, the way you count degrees in E. And I extend Q naught by, in general, an infinite sequence of higher maps that go from an nth tensor power of the vector space E back into E. They're going to be graded antisymmetric maps, and they're going to satisfy some rules which define an L-infinity algebra. Okay, so the first rule is again a compatibility condition between Q naught and the first bracket L2, which is like a Leibniz rule, a graded Leibniz rule again. Or if you like homotopy algebra, it means that L2 is a cochain map. The next relation is, so you take L2 and you iterate it. So the thing on the left-hand side is the combination you would write in checking the Jacobi identity for a bracket, right? And in general, it's violated. It's violated by Q naught and the next bracket in your list, L3. Okay, so the Jacobi identity is violated, but it holds up to homotopy. Or equivalently, the Jacobi identity holds up to some cochain homotopy, which is L3. And then there's in general an infinite sequence of these types of higher homotopy Jacobi identities. And that's an L-infinity algebra. And I'll be interested in cyclic L-infinity algebras, so we'll demand that this has a pairing on it. So again, a non-degenerate inner product into the complex numbers, and it's cyclic in this. So cyclic means you just move this string of V's through the slots. So we bring the Vn over to the first one and move V0 into here. Again, with some grading factors sitting in the front. So a one-line definition of what an L-infinity algebra is, it's a coherent, homotopy coherent generalization of the Lie algebra. Okay? And cyclic structures are things like invariant inner products on the algebra. So a cyclic L-infinity algebra is a homotopy coherent generalization of a quadratic Lie algebra. Okay, so one other technical thing you can do, you take your L-infinity algebra. Now, this symmetric algebra is a graded commutative algebra, and the tensor product of any L-infinity algebra with a graded commutative algebra is also an L-infinity algebra, just like the tensor product of a Lie algebra with a commutative algebra is also a Lie algebra. Okay, and the way you extend the structure is if you take the string of elements in the tensor product, you just pull out the elements that are in sim E1 and evaluate the bracket on the V's, which are sitting at E1. And similarly for the pairing. Okay, you just pull out A1 and A2 from the pairing, and that is the extended pairing.
Now your pairing is not C valued anymore.
This is sim valued now.
Yeah.
Yeah, so it's not valued, it's not an L-infinity algebra over C, but the axioms are still satisfied.
You always assume that you have some sort of absolute Z gradient.
I have what, sir?
I mean, you have absolute Z gradient, so you can't work, let's say, this relative gradient, so there's like more complicated than just Z gradients. Q gradient.
No, this is, everything's Z graded here.
Z gradient.
Everything's Z graded.
Absolute Z gradient.
All Z graded, yeah.
Okay.
And you can, of course, specialize in things like Z2, but everything in general is Z graded. Okay, now we can define interactions. So interactions are these elements sitting in degree 0 in the symmetric algebra. And the way they're constructed is what you do is you take dual basis. So you take a basis for my vector space E minus 1, and you look at a dual basis, dual with respect to the pairing, the inner product that I've defined. And then you can define these things called contracted coordinate functions. So you take the dual basis, the basis sum over the indices in that basis, and that you can show gives an element in this tensor product in degree 1. And now you apply this extended L infinity structure to those elements, and you define an action functional, which is called the homotopy Mark-Cartan function. Okay, so lambda here is just some constant. So it's going to be play the role of like a coupling constant. And this is the thing you write down. So if I take that term and I add to that the bracket, extended bracket, which pairs the contracted coordinate function A with the free differential acting on A, I get another action functional that's called the BB action. So lambda equals 0 gives you the free theory.
So can I ask, how do you derive the interaction term? It's put from the first instance, and only then verify the Markov equation is satisfied, or?
But yeah, so I write this down, and now that was what I was going to say next. Now you can check that this master equation is satisfied as a consequence of the homotopy Jacobi identities. And that translates into saying that if you take the free differential, you perturb it by this interacting part, which is just this Mark-Cartan action in one slot of this kind of Poisson bracket, and you let the remaining slot act on something. So that gives you another operator. It tells you that squares to 0. So you get another differential out of this, and so you get another P0. Okay, so this triple here is now a P0 algebra, and we have sim E1, and now this Qint here. And that's the P0 algebra of observables for this interacting. Okay, those are the interactions. Okay, that's all classical. So how do we quantize the theory? So to quantize, we're going to introduce an object, and the role of this object is going to be to define a notion of Gaussian integration, or in other words, to give me Wick's theory. That's how you do quantum field theory. And so physicists do quantum theory. They use Wick's theorem over and over again to calculate it. It's the only thing you really need to do. Okay, so define what's called the BB Laplacian. So it acts on this algebra of observables, sim E of 1. Takes me into that up to some degree shift again. And it's defined by these conditions here. So on the unit element of sim, it's 0. On any single primitive element of sim E of 1, so anything that just sits in E, it's 0. And if you take the product of two primitive elements, it returns this bracket of two elements. And in general, the product of two elements, there's this rule that it satisfies, which is not quite a Leibniz rule. So this is not a derivation, because there's an extra term there that involves the bracket. Okay, but that's enough to uniquely define what delta BB is on all of sim E of 1. And then later on, I'm going to write down an explicit formula when I come to the grader theory. Okay, now you check some things. This is graded commutes with the free differential squares to zero and annihilates this interaction action that I wrote down before. And again, it means that if you combine everything we have so far into a new differential like this, where I put an H bar in front of delta dV to sort of emphasize that this is coming in the quantum theory, then this also squares to zero. And so this defines the quantum observables, and you might say, oh, there's another P0 algebra. It's not a P0 algebra because the derivation property is lost. Okay, so I don't put the bracket in here. It defines something called an E0 algebra, which is a cochain complex with a distinguished element. In this case, the distinguished element is the unit. But those are the quantum observables for the interactive BB. Okay, so that's how we quantize. And now how do we calculate things? So in physics, we want to calculate correlation functions. And that's usually where path comes. But you can do it without path. Okay, and use something called homological perturbation theory. So what's going to happen in a field theory is, so the statement is that the propagators of a field theory are going to determine what's called strong deformation retracts of the dual. What does it mean? So we look at two things. We look at two cochain complexes. We have the original cochain complex E with some shift in degree, Q naught, and then we've got the cohomology of the cochain complex, which is this H bullet E. Okay. And then on that complex, the differential is trivial because it's the cohomology. And then I asked that there is a triple of maps, iota, pi, and gamma, and they satisfy some conditions. Okay. Which I'm not going to explain in detail. They satisfy these conditions, and that defines something called the strong deformation retract. And as usual in topology, strong deformation retract is meant to, you think of this as saying that the two things are homotopy. So they're not the same, but they're homotopy. Okay, so you have and that's an assumption. It's not something that's you have to construct this. Okay, the only thing we're going to have when we have a field theory is what gamma is, and then you have to find an iota and a pi that satisfies this. So its existence is not guaranteed, but that's what we're after. So what we do now is we take that, we pass to the observables. So instead of looking at cohomology of E and E, we look at the symmetric algebra on cohomology and symmetric algebra on E. And you can extend these maps. You can extend the maps that originally appeared to other maps, and there's formulas for them. I'm not writing them down, but there's explicit formulas how to extend. And the key thing now is something called the homological perturbation limit. If I define a perturbation of this form, which is just this combination delta here is the thing that appeared before when I went from the free theory to the interacting quantum theory. And I assume that that's something called a small perturbation, which means that when I write power series with it, they converge. At least it makes sense as form of power series. It says that then there exists a strong deformation retract. So what's happening? I take Q naught and I add to it delta. I perturb it by delta, and that gives me what I call QBV on this side. And now it says that there's a deformation retract where I've put tildes over these maps now, and a new operation here, which is no longer zero, acting on the symmetric part of the cohomology. That's a theory. That's the homological perturbation law.
Why is homological if you deal with cohomology?
There's this kind of weird thing that goes on. People call things homological and cohomological because there's conventions where you use homological.
I'm just kidding.
No, it's a good question. Anyway, and there are explicit formulas for these maps with tildes on them. I don't need all of them, but I'll just tell you what pi tilde is, because that's the one we're going to use. Okay, so it's given in terms of the maps from the middle there on the observables by this formal formula, where you understand this inversion as a formal power series. So now if you take a string of elements over here, you act on it with the projection pi tilde, you get something in sim E of 1, and the claim is that those are the endpoint correlation functions of your field. That looks a bit weird because they don't look like numbers, right? They're polynomials on this cohomology. But if you think for a moment, if you're a physicist, you think for a moment how you do perturbative quantum field theory. If you have a theory that has more than one vacuum, vacuum is not unique. You have to pick a vacuum to expand it. That's the only way you're going to get a number. So once you pick a vacuum here, so you let this act on something in there, then you get vacuum. And again, just a moment's thought tells you that this is really the space of vacuum, right? Because it's the cohomology of the field of the free field theory, and that's how you define vacuum space in quantum field. Look at say the solutions of the free field equations. So these are the correlation functions on the space of vacuum of the field theory, and you've got a definition of quantum field theory that never refers directly to a path. Right, okay. I wanted to go slowly through that because I think the brain part will be able to go through quicker. But let's do an example. So as I said, I'm only going to look at these things called fuzzy field theories. So what the classic example of fuzzy space is the fuzzy sphere. So the fuzzy sphere is it's a matrix algebra. It's an n by n matrix algebra, but a special kind. You take the spin j, where j is n minus 1 over 2, representation of SU2, okay, and you take the tensor product of that representation with itself. So as a vector space, it's just the algebra of n by n matrices, but of course it carries actions of SU2 on either side. And then we'll call the generators in that representation, and generators of SU2 in that representation, xi, xj. They satisfy those commutation relations. They're Hermitian, so there's Hermitian conjugation on the algebra of complex matrices. And the sum of their squares is 1, the identity matrix. And that's the sense in which this is a sphere, right? Because there are 3 x's, because it's SU2. And so and the sum of their squares looks like the equation for a sphere in R3. So that's called the fuzzy sphere. And then you think of this as a finite dimensional approximation to a sphere. So this is the finite dimensional approximation to the functions on a sphere. And now you just turn the machine. You make some choices and you turn the machine. Okay, and I'm only going to talk about scalar field theories. You can equally treat gauge theories, but they're a bit more involved. But just to illustrate things, I'll do scalar. So the free BB theory now is a complex with only 2 non-zero entries, which are both equal to A. So these are going to be the fields of the theory and their antifields. Because it's a scalar theory, there's no gauge symmetries. The rest of the components would include the gauge symmetries. So it's a scalar theory. So the natural thing for the free differential is to take some Laplacian, and I want to look at massive scalar fields here, just for simplicity. So I put a mass squared term in. And the delta is something called the fuzzy Laplacian. Okay, so it's defined by this double commutator there with some normalization. And the way you think of these x's, you just think of them as kind of curved or covariant derivatives on the sphere. So this is really something like a Laplacian. And then there's a natural linear product that's given by the trace of the product of 2 matrices, again with some normalization. And just like if you were on an ordinary two-sphere, there's a notion of harmonics, harmonic functions with spherical harmonics, which are eigenfunctions of the usual Laplacian on the sphere. Well, there's a notion of fuzzy spherical harmonics. So they're things which diagonalize this Laplacian. They have some normalization addition. So I'm going to use those. These could be explicitly constructed, but I don't need the formulas. Now we want to go to the interactions. We'll define an L-infinity algebra. For any n greater than or equal than 2, I could choose these n brackets by taking a string of phi's, which are matrices, and multiplying them together. But that's not all I need to do, because the L-infinity brackets have to be symmetric, graded symmetric. But in this degree, if these are sitting in degree 0, it has to be symmetric. And these are matrices, so they don't commute. So I have to symmetrize. That's what this sum over permutations of the labels does. This makes it symmetric. So that's now a symmetric product. And now I can introduce interactions as before. I take these fuzzy spherical harmonics. I look at their, as a basis, you look at their duals, sum over everything, evaluate the bracket using the pairing, and I get this type of a formula here, okay, involving the dual spherical harmonics. And these i's here are given by inner products of this form, these formulas here. And I'm not going to write them down, but there's, again, explicit formulas for them, given in terms of the Wigner 3J and 6J symbols for SU2. But I don't need the formulas, but they can be written down explicitly. And these are symmetric. These are symmetric. If you take any neighboring pair of indices and swap them, these are symmetric. Okay, so now the deformation retracts are very easy here. And this is why I introduced this mass, because if you put this mass squared into the Laplacian, it has no zero modes. Kernel's trivial. So the cohomology of that cochain complex is trivial. So this deformation retract I had before looks like this. So the part involving cohomology is just 0. The propagator, which is the inverse of my free differential, is still there on the right hand side, but then the two maps, the projection to cohomology and the inclusion are just 0. It's a very, very simple example, but it's non-trivial. It gives you non-trivial. Now extend that to the symmetric algebras and put the perturbation. Put the put the perturbation in. Then I get something which looks like this. On this slide. And the symmetric algebra of 0, the 0 vector space is just the complex. So now when I calculate correlation functions, I really do get numbers because the vacuum is unique here. There's only one vacuum state. And moreover, the key property of this capital pi that I wrote down before is that it's only non-trivial when it hits the unit element in the symmetric. And that's because the projection in the original retract is 0. I haven't shown you the explicit formulas for everything for you to see that, but that's what happens here. So that makes the calculations, it's easy to identify what calculations you should do. So for example, let's say you want to calculate the 2-point function at one loop in phi-4 theory. So you put n equal to 3, what we wrote before. You calculate this thing here, where delta, remember, is the perturbation of Q0. And you sit down for however long it takes you to calculate these things, an hour or something, and you get a formula. Okay, so this is the kind of, this is the non-interacting piece, right? Doesn't depend on lambda, so that's like the free propagator. Remember, G is the propagator, and then you get the interaction term at this order, lambda squared. Okay, these come from of course, the eigenvalues of the free propagator. So there's an explicit formula you can write down, and you just show that agrees with what people calculated from traditional quantum field theory. So this is more of a sanity check, right? That this formalism work, because you can argue, why would you need to go through BV here, because you have a path to go. Finite, it's a matrix algebra, right? So you can define things rigorously, but so this is really just a check that it all works. Okay. Are there any questions? Because I'm going to quickly go through the gradient stuff, because as I said, it's
so what's the dependence on L infinity structures that we choose, right? So this
well, in these i's depend on the L infinity structure.
So So if you choose different, say, LNP structure, what can
You get a different interactions, right?
So you would, okay, that's.
So I fix, and in principle, also the Q, so the Q naught, I say fix. So I'm saying I got scalar field theory. So, scalar field theory, I know it should be a Laplacian. And then I'm free to perturb that with whatever I want.
So it's not like a minimal model for LNP.
Well, that's what that is, right?
I see it.
But these are the minimal
I
ones.
see, yeah.
I didn't say that, but that's what
I see.
it is. Any other questions? Yes.
So can you please give a hint on how to handle the masses?
The massless case, there are zero modes of a little particle. We can actually classify what they were. And then you get something non-trivial on this side here. So instead of C, you're going to get some vector space or the symmetric algebra on some vector space. And you go through the calculation in exactly the same way, but what you need to do is sort of mark these external legs to indicate that they're functions. They have to act on a vacuum. So as I said before, you get something which is not a number. This is a number, but in general, you get something which is not a number. It looks formally like a number because it still involves these brackets, but these now have to be thought of as functions on symmetric. But it's the same, it's more or less the same calculation, but the other thing that will change is this. You have to change the definition of the projector. Because now, when the cohomology is non-zero, this projection up there, the zero that goes into 0, 0, that's the projection, is no longer zero. So several things change in the calculation, but it's still a very doable calculation. The formulas are the same, but the detail, this property that only pi of 1 equals 1 is non-zero is no longer true. Okay, so now we're going to go on to the braided stuff. And Brano said I could have what, 3 hours to talk this? I'm not going to go 3 hours though, but I'm going to go slightly over an hour.
But not exactly both.
Oh, sorry.
I don't mind.
I'll go over an hour, but I won't go 3 hours. Okay, so let's now go and start thinking about these graded theories. So here's the idea. The BB formalism or the L-infinity algebras. What we've done is we've defined them in a special symmetric monoidal category. So the category of vector spaces with the trivial braiding, right? But these definitions actually make sense more generally. You can define them in any symmetric monoidal category, provided it's closed in abelian, but let's not worry about that. But any symmetric monoidal category, even one with a non-trivial braiding isomorphism, and we can define braided notions of the braided BB formalism and braided L-infinity algebras. And the braiding comes here just because whenever I define things, I have some notion of a graded symmetry, right? And that still makes sense, but in a braided sense. So things aren't on the nose symmetric or anti-symmetric, but they're controlled by some braiding. And I'm looking at a very particular type of symmetric monoidal category, and that's the category of vector spaces, which are, say, left modules for some triangular Hopf algebra. So those are going to be the objects, and then the morphisms in this category are going to be the equivariant groups. Okay, so triangular Hopf algebra means there's some quantity in the tensor product called an R matrix, a universal R matrix. Okay, and I'm going to write it in the symbolic form, meaning that because it's in the tensor product, it's a sum of elements whose legs live in H tensor range. Okay, so that's what the notation means. And triangular means this is invertible, and its inverse is equal to the same element where I swap the two legs. Okay, so R minus 1 is R2. So you swap these two legs there. That's what triangular means. Now, given an R matrix, you can define a braiding isomorphism. which says if you have two Hopf algebra modules, you can swap them, but you need to swap them in a way which is compatible with the action of the Hopf algebra. Okay, so these triangles denote the actions of the Hopf algebra H on the respective vector spaces. And then tau R just says to swap W and V, but when you swap anything now, you have to insert these R matrices. It's always symmetry up to the braid, right? And the point is that this is symmetric. Symmetric means it squares to 1 if the R matrix is triangular. And that's where I need triangularity. So the key question here is how do you go beyond the symmetric assumption? So in particular, how do you deal with quasi-triangular algebras? And that's something I was talking with Thomas Weber when he was here. So I've been thinking about that, but it's somehow puzzling how to do that. But anyway. Okay, so this is the setup. We imagine now we're in this category and we go and define everything. And you almost don't have to write down formulas. You just say this is symmetric, this is anti-symmetric, because now symmetric has a very specific meaning. When when you say symmetric in a category, you mean with respect to whatever braiding I have in there. So it's so straightforward. So again, I start with a Z-graded vector space, but now it's a module. Because everything's going to be objects in this category. I'm going to have my Q0. All my maps now are going to be morphisms in the category. So it's going to be an H equivariant differential of degree 1. I'll have an inner product, which is now going to be H invariant. And now the graded anti-symmetry gets replaced with the graded anti-symmetry. So that formula there. It's not graded anti-symmetric, but you have to insert R factors. Okay, so the calculations definitions and calculations are very easy here. You just have to keep an eye on whenever you swap things. And every time you swap things, you insert R matrices. Okay, now you want to introduce some observables. You introduce the braided symmetric algebra, which I'll distinguish in this case with the symbol R. And the multiplication in there is no longer symmetric, but it's braided symmetric. That's what changes from the usual case. So again, you have to insert R matrices. And now you define a triple that satisfies the axioms of a braided P0 algebra. So the compatibility condition doesn't change. Braided symmetry changes because you're swapping, you insert R's. Braided Jacobi identity changes because when you start rewriting brackets here, you have to flip things. That introduces R's. And finally, the braided Leibniz rule changes because when you pair phi with psi here, there's no interchange. But when you want to pair phi with chi, you have to first swap phi with psi. So you get some extra braiding factors in there. Okay, and now comes the notion of braided L-infinity algebra. You extend this cochain complex by, again, anti-symmetric maps, but now you want them to be morphisms inside this category. So they're braided anti-symmetric. And so they form something called the braided L-infinity algebra. So the graded anti-symmetry is replaced by braided anti-symmetry. And then you have your infinite tower of harmonically Jacobi identities, which you write down. And again, they're going to involve grading factors.
Oh, if you write down the braid Jacobi identity,
Yeah.
Because you can write Jacobi identity in many forms.
Yeah.
Using anti-symmetry.
Yeah.
So does it matter which one or you choose one particular like?
I don't think it matters. I think you can write down the trick is to write down the usual Jacobi identity and at the level of maps.
Yeah, this derivation.
No, but I mean, don't write down the formula when you evaluate on a string of vectors. Write it down saying the maps satisfy, and that there's no ambiguity there, right?
Yeah.
And that's actually how we define the Jacobi identity, because then what that formula involves, it involves some flip maps.
Yes.
Right? Swap things, and then of course you just deform the flip maps. So, but no, there's no ambiguity as far as I can tell. Okay, so that's a braided L-infinity algebra without writing the pages of axioms. And what are these things? So I said L-infinity algebras were some generalizations of Lie algebras. Well, the braided L-infinity algebras are homotopy coherent generalizations of things called braided Lie algebras, which we studied again over 30 years ago. They were also called quantum Lie algebras in the quantum roots literature. But these are sort of a generalization of that. Again, we all want to define a notion of braided cyclicity. We've got some inner product, and now the cyclicity changes, and you see you get R matrices. When I start moving things around, I'm really swapping things as I do that, right? And whenever I swap, I have to introduce R matrix factors. You introduce an R matrix factor for every transposition that you do in a permutation. Okay, and then there's again an extended L-infinity algebra. The SimR is a braided graded algebra, braided graded commutative algebra. And if you tensor that with your braided L-infinity algebra, you get another braided L-infinity algebra. The formulas look formally the same as before, but there are R matrices now. Because the formula I wrote before, what did I do? I took out A1 and I took out A2. But now you see if you're pulling out A2, you have to pass it over V1. So there's again an interchange involved there. So you get these R matrix factors coming in there. And so on. Okay, braided quantum field theory, we just do the same, turn the same crank as before. Okay, we start with these contracted coordinate functions. We just insert some R's where there weren't R's before, and you write down this object. Now you get your braided P0 algebra of observables for the interacting theory, and you introduce a braided BV Laplacian. Okay. And the braided BV Laplacian, now if you write it out explicitly, you write the similar axioms to what I had before. But remember, I had this derivation-like property. When you write the derivation-like property, you're again swapping at some point. So there are R matrices involved. And if you iterate that definition, you can write down a general formula for how delta BV acts on a string of elements in the vector spacing. And it looks like this, okay? So it always reduces to some products of fields and then some brackets, some inner products, right? And you see it's summing over all possible ways of pairing two elements, and it introduces R matrices, because every time you want to pair two different elements in the string, you have to do some swaps. So that's where these R matrices come from. And this is the gadget that's going to take care of the notion of braided Gaussian integration and ultimately the braided Wick's theorem that Ockel talked about many years ago. Okay, and then again, there's a braided E0 algebra of quantum observables for the braided field theory. So the slides are very easy to make for these talks, right? You take your old slide and just put braided everywhere. But there is content. You do see some effects to it. But as I said, it's very straightforward. Okay, finally, how are we going to do calculations? We'll come to an example in a moment. So again, we want a notion of the homological perturbation lemma, and we just sort of put this thing in a different category, right? Put this strong deformation retract in a different category. We get a braided strong deformation retract. Same thing as before, same axioms, but now you demand that the pi and iota are H equivariant maps, and that gamma, your contracting homotopy, is H invariant. And then you can go to the symmetric algebra. You can prove that if you take a H invariant perturbation of Q naught, you can go and prove, it's a proof, it's a proposition that again, you have a braided strong deformation retract on the braided symmetric algebras of the original vector spaces. Okay, it all looks the same as before. That's the result. So there's a version of braided homological perturbation theory that carries easily over to the braided place. So this is the upshot, because I was trying to motivate part of this talk by saying, how do you define how do you find correlation functions in braided quantum field theory? And this is the answer. Braided homological perturbation theory computes correlation functions with the path integral of braided quantum field theory. So let me just conclude in my last few minutes with an example. So this is now, again, I'm just going to do scalar field theory, but we're not going to look at the sphere. We're going to look at something called the fuzzy torus. Okay. So again, the fuzzy torus formally, the algebra functions on this as the n by n matrix algebra over the complex numbers. And there are two generators I call U and V. So you can actually write any n by n matrix like this. So a general element of the algebra is written as a sum indexed by the cyclic group of order n. And these generators, well, they're Hermitian, satisfy some Hermitian law. Their nth powers are the identity matrix. And they don't commute, but they kind of Q commute. So they commute up to this Q factor, which is a primitive nth root of unity. And you don't need anything more. You just take this as the abstract definition to do calculations. But you can explicitly realize U and V by things called clock and shift matrices. If you know what those are, then there's explicit formulas for what U and V are. Well, you don't need them. And there's a natural trace on here where if you take an element, expand it, you just read off the kind of constant coefficient there when you put both indices there. So it's kind of the constant term in that expansion. So you think of U and V as the kind of the primitive plane wave, the exponentials on the ordinary torus. Okay? And then this trace is what you would get if you integrated a function over the torus, right? You just get the constant part function. Okay, now this has more structure. This also carries the action of a triangular Hopf algebra. So the Hopf algebra is you take the finite group Zn2 and you look at its group algebra. I'm not going to write down the Hopf algebra structure, but it acts on A by these formulas here, on generators. So you take a pair of integers inside the cyclic group, and on U it takes Q to the power of the first entry, and on V Q to the power of the second. The triangular structure, it's a triangular Hopf algebra, is given by this R matrix here. So this is the formula. You sum over all pairs of vectors S and T. There's some Q factors in front where this wedge just means a sort of standard skew pairing of two-dimensional vectors. Right? And again, I call that R alpha tensor R alpha. And this makes this algebra, you check it, it's a calculation that this becomes a braided commutative algebra, braided H-mod, commutative H-module algebra. So it means that you take two matrices, of course, the matrices don't commute, but when you swap them, you just insert the R matrix factors. So it really is a type of commutative, but it's a braided commutative. Okay, so off we go. We define the free braided field theory. This is the vector graded vector space of the complex. In both slots, I put A because it's a scalar theory. There's no gauge symmetries. Again, scalar theory, I'm going to take the Laplacian plus some mass term. And now the Laplacian looks like this. It looks sort of the same as before. So again, you think of these kind of adjoint actions as acting like derivatives, right? So this is like the sum of squares that defines the Laplacian. There's some convenient normalization factor in front. And then again, the cyclic structure, the inner product is again given by the trace with some normalization.
Excuse me.
Yeah.
So, concerning the last couple of points, so isn't the case that Q0 is close to zero exclusively because of the gradient reasons? So there are no.
Yeah, exactly. Yeah, it looks weird, right? It doesn't look, and it's because you have a two-term complex. So you think that you've got yeah, I know this looks weird when you first see it. So I'm saying I have like an E0, a Q0 into E1. And then normally you would say Q0 goes into E2, but that's zero, right? So Q0 squared is 0, just by degree reasons. That's what you're asking, right?
Yes.
You're asking how on earth is delta plus m squared 0? And it's not a square, right? It's a composition.
Yeah, just to make sure there are no, the defining identities for positors do not appear anymore.
No, but I mean, what I'm saying is, I mean, the thing you want is Q0 composed with Q0
Yeah,
is 0, right?
I'm looking for
And
great.
it's strictly for grading reasons. You're right. Yeah. And it looks a bit weird when you see it because some of that Laplacian doesn't square to 0. That's not what we mean by squaring to 0. Okay. So let's again go and turn the crack. We introduce a basis. So these things called fuzzy plane waves. Okay, so you get some vector cyclic integers. We define the plane waves. And then again, you just work it. You find that these diagonalize that Laplacian. They satisfy some kind of orthonormal condition. And these numbers with the bracket q's are things called Q numbers. Okay, now here's a key point. For the braided L-infinity algebra, again, it's a scalar field theory. We choose the brackets, we take a string of n matrices. I take their products, but I don't symmetrize it. Because now I want braided symmetry. When I swap two things, I want R matrices there. And I already said that the algebra here is a braided commutative algebra. So when I swap two phi's, I'm going to get the R matrices that I want. So I don't sum over here, because now I've got the right symmetry. Okay, then everything is before. Construct the interactions like you did. You use this basis of plane waves now. And these interaction terms look explicitly like this. You can actually evaluate this inner product very simply now. And this has a very different symmetry than the thing I had on the fuzzy sphere. Okay, now it's Q. If you take a pair of neighboring indices and swap, you get some Q factors. Okay, now, deformation retract again. If m squared is non-zero, the cohomology of that Laplacian is trivial, and you formally get the same setup you had before, and things are trivial. This is my last overhead coming here. So again, to calculate correlation functions in this instance, it's very easy. The only projection that's non-zero is when you hit the unit element in the symmetric algebra. And just here are a couple of examples. So if you look at the free braided scalar field theory, so put lambda equal to 0, calculate the 4-point function. Okay, and again, you just kind of turn the crank to do this. And you get what looks like the expected Wick's theorem for a 4-point function, right? The different ways of pairing the fields into 2-point functions, but you get some R matrices appearing. So it's really a braided version of Wick's theorem. And it agrees with what will come. Second example, and again, try to look at the 2-point function at one loop. You do your calculation. And I'm just not going to point out details in the calculation. The point was to show you that there are explicit formulas that come out of this. It's not just formulas. There are things you can get. And there's some interesting observations to make about this type of theory. It looks very different than what you would expect in a conventional 2-point function at one loop in non-commutative field theory, where you would have a notion of planar and non-planar diagrams. There would be some phenomenon called UVIR mixing. And it looks like these theories behave very differently than the ordinary counterparts. And it suggests that these theories behave very nicely in their commutative analogs. And that's something we've been working on now. So if you know commutative field theory, it looks like these theories don't have this thing called UVIR mixing. That was suggested many years ago based on some more ad hoc arguments from people who were trying to describe what is a Brady quantum field theory. But in recent work, we've shown that that seems to be the case. Okay. I'm sorry for going over time.
Thank you very much for your time for your questions.
I have a question. How close that you have a young box equation?
Well, I mean, it's used, just used along the way. I mean,
Well, I mean, if, for example, I have a monoidal category, I have a collection of initial transformation between answering the
Yeah.
opposite direction. They don't.
no, I don't need the Yang-Baxter convention. It isn't you're asking, is it crucial? It's not crucial. But it's helpful.
Because in this way, for the case of quasi-declarant, how obvious you can go for the.
So if I use symmetry, that's not the.
Yeah, but you can construct following the recipe of G the boundary structure, it will be not satisfy Yang-Baxter anymore, but it will be some symmetric constraint of the category. So it will be now no braided category, but bounded category. It has some property
What category?
to boundary.
But then you don't have the grade.
But you still have this generalization of a flip map. It's squares to identity, but just doing it's the Baxter equation.
Okay, I don't know this construction, but
In the case of, for example, quantum groups, your R matrix has value eigenvalues q to some power plus and minus. Now this normalization will give, if you have q to the new structure, you have an eigenvalue plus one, if the R matrix had an eigenvalue q to the some power and minus one. There is some theory of quantum symmetrical and stereo algebra in this sense.
okay. No, I didn't know these.
Very common, just you get a representation of the braid group or the cactus.
In this case, right. Well, here also, I don't really have a representation of the braid group, right? This is just a representation of the symmetric group, and that's what I want to have, is a representation of the braid group, but I'm only getting the symmetric group. So that's the cactus group. I don't know what the cactus group is, so you can tell me anything.
Richard, is it good or bad that you don't have UV?
Well, it's of course good.
It's good.
Yeah.
You consider it to be good.
Well, sure, because UVIR mixing spoils renormalizability.
Because people used to say that's the only interesting thing about the non-commutative field theory.
Yes.
Is there a way to make sense of something that can be regarded as a first order approximation to braided fields? What I mean is something that would use the data of a classical.
Yeah, yes. So Thomas Weber gave this last week, right?
Previously, he did talk about infinitesimal.
Yeah. I don't know. The first time I heard about that stuff was from Thomas.
Okay, any other question? I finish the question part by my more or less kind of low growth question on what's the most significant physical application which might be set from your side of view when it comes to braided infinity, or when you formulate this EV in a braided setting.
What's I didn't quite understand the question.
What are the most significant applications to physics?
This is one of them here.
Okay.
And no, it really is, because UVR mixing is a problem that the one consequence of that is that the theory is not renormalizing. And it's not known in scalar field theories, it's known how to cure this by modifying the action. But in gauge theories, for instance, it's not understood. So the only time there isn't UVR mixing in the standard theories is when you do this modification of scalar theories, or when you have enough supersymmetries. Some supersymmetric theories also, but in general they will. So from a field theory point of view, that's the most interesting thing. The other thing I didn't talk about is the notion of gauge symmetry is very interesting in these theories, because it's not an ordinary gauge symmetry, it's a braided gauge symmetry, and that comes with all kinds of unusual things as well. The braided gauge transformations, they don't behave as derivations, they act like braided derivations. The moduli spaces are very classical solutions. Moduli space are classical solutions. Modular gauge transformations is a very strange looking object, and so there's a lot of interest even at the classical level. Once you put gauge symmetry into the game, it's very
And
interesting.
could you name some researchers who were active on doing braided gauge theory?
Stories.
What are papers which deal with this braided kind of?
Well, you could look at my last few papers. As I said at the beginning, this notion of braided gauge symmetry was looked at in the early 90s by Brzezinski and Majid. So there's some early works on it as well. It's not a huge topic yet.
Okay. So thanks again for your replies. That's all.